Partial discharge, or PD, testing is a critical aspect of assessing the health and reliability of medium voltage cables. There are two primary methods for conducting these tests, online and offline, each with its own set of procedures, advantages, and applications. Understanding the differences between these two approaches is essential for effective cable maintenance and diagnostics. Online partial discharge testing is conducted while the cable is in service, without any interruption to the power supply. This is a significant advantage as it allows for continuous or periodic monitoring of the cable's condition without taking it out of operation. The process involves placing sensors on the cable sheath or core to detect partial discharge signals. These sensors are designed to pick up the faint electrical signals emitted by PD activity within the cable insulation. Because the cable remains energized during the test, online PD testing provides a real-time assessment of the cable's performance under normal operating conditions. This makes it particularly suitable for condition monitoring and predictive maintenance. By continuously monitoring PD activity, potential issues can be detected early, allowing for timely intervention and preventing costly failures. Online PD testing can also help identify the sources and locations of partial discharges without requiring a cable outage. However, it's important to note that online PD testing typically has lower sensitivity compared to offline testing. This is due to the presence of background noise from the energized system, which can interfere with the detection of PD signals. Despite this limitation, online PD testing remains a valuable tool for assessing the overall health of medium voltage cables and identifying potential problem areas. Offline partial discharge testing, on the other hand, is conducted with the cable de-energized. This means that the cable must be taken out of service and disconnected from the rest of the system before the test can be performed. Offline PD testing involves applying a high voltage to the cable and measuring the resulting partial discharge signals. The high voltage can be either very low frequency, abbreviated VLF, or direct current, abbreviated DC, depending on the specific testing requirements. Because the cable is de-energized and isolated from the system, offline PD testing provides a more controlled environment for measurements. This results in higher sensitivity and allows for more detailed information about PD characteristics such as magnitude, phase angle, and frequency. Offline PD testing is often used for fault location, cable diagnostics, and acceptance testing. It can help pinpoint the exact location of insulation defects or other issues that may be contributing to partial discharge activity. Additionally, offline PD testing can be used to assess the overall quality of a cable and ensure that it meets the required performance standards before it is put into service. One key difference between online and offline PD testing lies in power interruption. Online testing does not require any power interruption, while offline testing necessitates the cable being de-energized. Another significant difference is in sensor placement. Online testing typically involves placing sensors on the cable sheet or core, while offline testing may involve placing sensors on the cable insulation or at cable joints. PD monitoring also differs between the two methods. Online testing allows for continuous or periodic monitoring, while offline testing is typically a single measurement. Sensitivity is generally lower in online testing due to background noise, while offline testing offers higher sensitivity in a controlled environment. Fault location is typically less precise in online testing compared to the more precise fault location capabilities of offline testing. The purpose of online testing is primarily for early warning and condition monitoring, while offline testing is used for detailed diagnostics and acceptance testing. Frequency of testing is another distinguishing factor. Online testing is often performed regularly, either continuously or periodically, while offline testing is typically conducted infrequently as needed. Finally, the cost of online testing can be high due to the need for continuous monitoring, while offline testing is generally less expensive due to its single measurement nature. In summary, online and offline partial discharge testing each offer unique advantages and are suited for different applications. Online testing is ideal for continuous monitoring and early detection of potential issues, while offline testing provides more detailed diagnostics and is often used for acceptance testing and fault location. The choice between the two methods depends on the specific needs of the application and the desired level of detail in the PD assessment. Consider the following aspects when deciding between online and offline PD testing. Firstly, consider the operational constraints. If it is not possible to de-energize the cable due to operational requirements, online testing is the only viable option. Secondly, assess the level of detail required. If a detailed assessment of PD characteristics and precise fault location are needed, offline testing is more appropriate. Thirdly, evaluate the available resources. Online testing may require a more significant investment in continuous monitoring equipment, while offline testing may require specialized high-voltage test equipment. Fourthly, consider the frequency of testing. If continuous monitoring is desired, online testing is the obvious choice. If only periodic assessments are needed, offline testing may be sufficient. Fifthly, take into account the criticality of the cable. For critical cables that are essential for maintaining system reliability, continuous online monitoring may be justified. Sixthly, evaluate the cable's history and condition. Cables with a history of PD issues may benefit from more frequent online monitoring. Seventhly, consider the regulatory requirements. Some industries or applications may have specific requirements for PD testing that dictate the use of either online or offline methods. Eighthly, evaluate the cost-effectiveness of each method. Consider the long-term costs of both online and offline testing, including equipment, labor, and potential downtime. Ninthly, assess the availability of skilled personnel. Both online and offline PD testing require trained personnel to perform the tests and interpret the results. Tenthly, take into account the safety considerations. Ensure that all necessary safety precautions are taken when performing either online or offline PD testing, particularly when working with high voltages. Online partial discharge testing offers the advantage of continuous monitoring without power interruption, making it ideal for assessing the real-time condition of cables under normal operating conditions. However, it is essential to consider the limitations of online testing, such as lower sensitivity due to background noise, and to supplement it with offline testing when more detailed diagnostics are needed. Offline partial discharge testing provides a more controlled environment for measurements, resulting in higher sensitivity and the ability to obtain detailed information about PD characteristics. This makes it a valuable tool for fault location, cable diagnostics, and acceptance testing. However, it is important to weigh the benefits of offline testing against the cost and inconvenience of de-energizing the cable. A comprehensive cable maintenance program should incorporate both online and offline PD testing to provide a complete assessment of cable health and reliability. By combining the strengths of both methods, potential issues can be detected early, and appropriate actions can be taken to prevent costly failures and ensure the long-term performance of medium-voltage cables. Factors influencing partial discharge. Several factors can influence partial discharge activity in medium-voltage cables. Firstly, insulation defects are a primary cause of partial discharge. Voids, cracks, or contaminants within the insulation can create areas of high electric stress, leading to PD. Secondly, voltage stress plays a significant role. Higher voltage levels increase the electric stress on the insulation, making PD more likely to occur. Thirdly, temperature variations can affect PD activity. Higher temperatures can accelerate the degradation of insulation materials, increasing the risk of PD. Fourthly, humidity can also influence PD. Moisture ingress into the insulation can reduce its dielectric strength and promote PD. Fifthly, cable age is a factor to consider. As cables age, the insulation can degrade, making them more susceptible to PD. Sixthly, load variations can impact PD. Frequent load changes can cause thermal cycling, which can stress the insulation and increase PD activity. Seventhly, mechanical stress from bending or vibration can damage the insulation and contribute to PD. Eighthly, chemical contamination from exposure to oils, solvents, or other chemicals can degrade the insulation and promote PD. Ninthly, improper installation practices, such as sharp bends or excessive pulling force, can damage the insulation and increase the risk of PD. Tenthly, environmental factors, such as exposure to ultraviolet radiation or ozone, can also degrade the insulation and contribute to PD. Understanding these factors and their potential impact on PD activity is crucial for effective cable maintenance and diagnostics. Regular PD testing, combined with visual inspections and other diagnostic techniques, can help identify and address potential issues before they lead to cable failures. Diagnostic techniques can supplement both online and offline testing. In addition to online and offline PD testing, other diagnostic techniques can be used to assess the condition of medium voltage cables. One such technique is insulation resistance testing. This involves measuring the resistance of the cable insulation to determine its integrity. A low insulation resistance value may indicate insulation degradation or moisture ingress. Another diagnostic technique is dissipation factor testing, also known as tan delta testing. This measures the energy loss in the insulation due to polarization effects. A high dissipation factor value may indicate insulation degradation or contamination. Partial discharge mapping involves using specialized sensors to locate the sources of PD activity within the cable. This can help pinpoint the exact location of insulation defects or other issues. Time domain reflectometry, abbreviated TDR, is a technique that uses electrical pulses to detect faults or discontinuities in the cable. This can be useful for locating cable breaks, splices, or other anomalies. Frequency domain reflectometry, abbreviated FDR, is similar to TDR but uses frequency swept signals instead of pulses. This can provide more detailed information about the cable's impedance characteristics. Thermography involves using infrared cameras to detect hot spots on the cable surface. This can indicate areas of high electrical stress or insulation degradation. Visual inspections can also be valuable. This involves visually inspecting the cable for signs of damage such as cracks, cuts, or discoloration. Oil analysis can be used to assess the condition of oil-filled cables. This involves analyzing the oil for contaminants or degradation products. Sheath testing involves measuring the voltage and current in the cable sheath to detect sheath faults or corrosion. Each of these diagnostic techniques provides valuable information about the condition of medium voltage cables. By combining these techniques with online and offline PD testing, a comprehensive assessment of cable health can be attained. Cable types and PD. The type of cable used can also influence partial discharge characteristics. Firstly, cross-linked polyethylene, abbreviated XLPE, cables are commonly used for medium voltage applications due to their good electrical properties and resistance to moisture. However, XLPE cables can be susceptible to PD if they contain voids or contaminants in the insulation. Secondly, ethylene propylene rubber, abbreviated EPR, cables are another popular choice for medium voltage applications. EPR cables have good flexibility and resistance to chemicals, but they can also be susceptible to PD if they are not properly installed or maintained. Thirdly, paper-insulated lead-covered, abbreviated PILC, cables were widely used in the past but are now being replaced by XLPE and EPR cables. PILC cables can be prone to PD if the paper insulation becomes saturated with moisture or if the lead sheath is damaged. Fourthly, high-pressure fluid-filled, abbreviated HBFF, cables are used for high-voltage applications and can also be susceptible to PD if the fluid becomes contaminated or if the insulation is damaged. Fifthly, solid dielectric cables, such as those made from polyethylene or polypropylene, can also experience PD if they contain voids or contaminants in the insulation. Sixthly, shielded cables, which have a metallic shield around the insulation, can help reduce the risk of PD by containing the electric field within the cable. Seventhly, unshielded cables, which do not have a metallic shield, are more susceptible to PD because the electric field can extend beyond the cable insulation. Eighthly, single-core cables, which have only one conductor, can experience PD if the insulation is damaged or contaminated. Ninthly, multi-core cables, which have multiple conductors within the same insulation, can be more prone to PD due to the increased complexity of the insulation system. Tenthly, submarine cables, which are used for underwater power transmission, must be carefully designed and installed to prevent PD due to the harsh marine environment. The choice of cable type should be based on the specific application requirements, taking into account the operating voltage, environmental conditions, and desired level of reliability. Regular PD testing and other diagnostic techniques can help ensure that the chosen cable type is performing as expected and that any potential issues are detected early. Mitigation techniques. If partial discharge activity is detected in medium voltage cables, several mitigation techniques can be used to reduce or eliminate the PD. Firstly, cable replacement may be necessary if the insulation is severely damaged or degraded. Replacing the cable with a new one can eliminate the source of PD. Secondly, cable repair can be an option if the damage is localized. Repairing the damaged section of the cable can restore the insulation integrity and reduce PD. Thirdly, cable injection involves injecting a special compound into the cable to fill voids or cracks in the insulation. This can help reduce the electric stress in these areas and reduce PD. Fourthly, cable grounding improvements can help reduce PD by ensuring that the cable shield is properly grounded. This can prevent the buildup of voltage in the shield and reduce the risk of PD. Fifthly, voltage reduction can reduce PD by lowering the electric stress on the insulation. This can be achieved by reducing the operating voltage of the cable. Sixthly, cable cooling can help reduce PD by lowering the temperature of the insulation. This can slow down the degradation of the insulation and reduce PD activity. Seventhly, environmental control involves controlling the environmental conditions around the cable to reduce the risk of PD. This can include reducing humidity, temperature, and exposure to chemicals. Eighthly, insulation coating can help reduce PD by providing a protective layer over the insulation. This can prevent moisture ingress and reduce the risk of surface PD. Ninthly, stress grading can help reduce PD by distributing the electric field more evenly across the insulation. This can be achieved by using special materials or designs that reduce the electric stress in critical areas. Tenthly, monitoring and trending PD activity can help identify potential problems early and allow for timely intervention. By monitoring PD levels over time, it is possible to detect changes in PD activity that may indicate insulation degradation or other issues. The choice of mitigation technique should be based on the specific cause of the PD and the overall condition of the cable. A comprehensive assessment of the cable, including visual inspections, PD testing, and other diagnostic techniques, can help determine the most appropriate course of action. Also, the cost must be taken into account. Implementing some mitigation techniques can cost significant amounts of money. Standards. Several industry standards provide guidance on partial discharge testing of medium voltage cables. Firstly, International Electrotechnical Commission, abbreviated IEC, 60270 is a fundamental standard that defines the terminology, test methods, and acceptance criteria for PD measurements. Secondly, Institute of Electrical and Electronics Engineers, abbreviated IEE 400.2 provides guidance on field testing and evaluation of shielded power cable systems using VLF technology. Thirdly, IEE 400.3 provides guidance on PD testing of shielded power cables in a factory environment. Fourthly, Association of Edison Illuminating Companies, abbreviated EIC, C8 specifies the requirements for extruded dielectric shielded power cables rated 5 through 46 kV. Fifthly, Insulated Cable Engineers Association, abbreviated ISO-93-639 outlines standards for 5 through 46 kV shielded power cables. Sixthly, IEC 60840 specifies test methods and requirements for power cables with extruded insulation for rated voltages above 30 kV, up to 150 kV. Seventhly, IEC 62067 covers test requirements for power cables with extruded insulation for rated voltages above 150 kV, up to 500 kV. Eighthly, ASTM International 1868 provides standard test methods for detection and measurement of partial discharge pulses and evaluation of insulation systems. Ninthly, SIGAR, the International Council on Large Electric Systems, provides technical brochures and guidelines on various aspects of power cable testing and diagnostics, including PD testing. Tenthly, local and national regulations may also specify requirements for PD testing of medium voltage cables. These standards provide valuable guidance on how to perform PD testing correctly and how to interpret the results. Adhering to these standards can help ensure that PD testing is conducted in a consistent and reliable manner. Safety. Safety is paramount when performing partial discharge testing on medium voltage cables. Firstly, qualified personnel should always perform PD testing. Only individuals who have been properly trained and are familiar with the equipment and procedures should conduct PD tests. Secondly, appropriate personal protective equipment, abbreviated PPE, should be worn at all times. This may include safety glasses, gloves, and other protective gear. Thirdly, high voltage safety procedures must be followed meticulously. Never approach energized cables or equipment without taking the necessary safety precautions. Fourthly, grounding is essential. Ensure that all equipment and cables are properly grounded before beginning any PD testing. Fifthly, lockout/tie-up procedures should be implemented to prevent accidental energization of the cable. Sixthly, warning signs and barriers should be used to alert others to the presence of high voltage equipment. Seventhly, regular inspections of the test equipment should be performed to ensure that it is in good working order. Eighthly, emergency procedures should be in place in case of an accident. Ninthly, thoroughly understand the testing equipment before starting the process. This is one of the most important steps to ensure the job is done safely. Tenthly, never work alone. Always have at least one other person present during PD testing in case of an emergency. By following these safety precautions, the risk of accidents and injuries can be minimized. PD testing is a valuable tool for assessing the condition of medium voltage cables, but it is important to remember that safety should always be the top priority.